Hi and welcome back to the next video in our series. Today we're going to be discussing wave behaviors. And there are 4 wave behaviors that we're going to be looking at: reflection, refraction, diffraction, and interference. But this video we're going to talk about reflection first. We've heard the term reflection all our lives when we look in a mirror and we see our reflection, and that's really the bouncing of a wave off of a surface. We look in a pond and see your reflection in the water, and you see your reflection in a mirror. But what is reflection? Reflection is when a wave travels to a new medium and part of the wave is redirected at the same frequency, at the same angle from the normal to the surface of the redirection. Very simply, this is when a wave bounces off of a material. It's that simple. But we're going to take a look at some examples of reflection. Here we have a diagram of reflection, and we have a ray coming in and hitting a surface and reflecting off the surface. This particular ray hits the surface against this dotted line called the normal line. Normal because it makes 90 degrees to the surface. This is the same normal line that we talked about way back in vectors when we talked about a normal vector. Sits on a normal line. So the angle is measured simply between the ray and the normal. That's theta I for incident. And when it bounces off at the same angle, theta R. Alright, let's take a look at the reference table and see what that is. Here we have the physics reference table, and we're on the wave section, and we've already discussed formulas 1 and 2, but here's formula W3. Theta I equals theta R. This is the law of reflection, and that is exactly what we discussed right here in this diagram. The angle of incidence, that's the incoming angle, is equal to the reflected angle, and it always must be measured against this normal. Now, here's a commonly asked question: why can't we just measure the angle off the surface instead of this normal line? And the answer to that is very simple. If your surface is curved, you cannot take an angle between a line and a curve and get the same angle at all different positions. So if we make a straight line 90 degrees to the point on the surface and take the angle between that normal line and the incoming ray, then that will always be accurate. Also, a ray is not a vector. This is not a vector. It is a ray, just like in math class. The arrowhead represents the direction the rays are moving. It's coming in, hitting this point, and bouncing off. Now here is something I wanted to address about these lines that you see on the ray. What are these lines? When looking at a ray, a wave ray, this could be a ray of light, or it can be any wave approaching a surface and reflecting off. These rays represent the tops of the wave crests. Let me show you in this diagram here. Okay, in this diagram, do you remember the sun chip? You open a nice bag of sun chips, you have a snack. The wrinkly surface of the sun chip is 3-dimensional. So the lines that you see on the ray, this red line represents the ray, there it is, and the black lines represent the wave crests, and the green dashed lines, which are not shown in that other diagram, represent the troughs. This is a 3-dimensional view, perspective drawing of what you see there. So that's what those ray lines actually mean. So I've put this little drawing in below here. This is what came off of the diagram, and you can see that this is expanded into a 3-dimensional view. Each of these straight lines represents the wave crest, here, here, and here. And of course, the 3-dimensional view, here's the actual sine wave itself. These are the crests, and then what's not shown in between these spaces, these little green dashed lines, they would be the troughs. And that's how that diagram works. In this simulation that I have open in front of you, I have a wave generator. So waves will start from around this yellow line right here, and they will come down the screen, and they will come down in parallel wave fronts. Let me show you what that's going to look like. Alright, so here they are. Each of these black and light blue lines represents a traveling wave crest. And what I'm going to demonstrate is the law of reflection. So I will clear the waves, and I will put a boundary somewhere over here. Now when these waves strike the boundary, they will obey the law of reflection. So let's take a look what we have. This is a boundary. The wave crests are flowing down the page. They will hit this barrier and then they will bounce off the barrier. That's reflection at an angle equal to their incidence. Let's take a look at that. There you go. Let me stop the wave for you. So you can see that these waves, they travel and they hit the surface, and then once they hit the surface, they bounced off at an angle equal to the incident angle. Okay, let's take a look at waves reflecting off of this barrier. So here they come in, and just as it's about to hit this barrier, you're going to see that the first part of the wave that hits the barrier is the first part to reflect off of the barrier. All the way through. So now take a look at these black dots right here. They all make a straight line. These lines here and here and here, those are the new wave crests. So the wave crest came in horizontally this way, hit the barrier, and bounced off. This is reflection. All right, let's take a look at another kind of reflection. This is two-dimensional reflection. Let's take a look at one-dimensional reflection. In this PhET simulation, I have it set so that a pulse can travel straight across the screen and out the window. Now I'm going to reflect this pulse on this line. So I'm going to change this to fixed end. I'm going to pulse, and notice what's happened. There is a reflection over this horizontal baseline. Let's look at this in slow motion. This is a fixed point reflection. So a fixed point reflection hits the fixed point, and the wave pulse flips upside down and reflects backwards. So this is also fixed point. It reflects and flips, and the process keeps going. Now, of course, in real life, if there's damping, as you see here, that would be energy loss, and the wave would not continue to travel forever. So this is a fixed point reflection. All right, let's take a look at another kind of reflection. I've changed the endpoint of this beaded string so that it has a hoop around this bar, and that's called a loose end or free end. So the first time was a fixed point reflection. This is a free end reflection. Watch the difference. So here it goes. There's your wave pulse. Oh, look at that. The free end went up and the pulse returned. Now the free end goes down and the pulse returns on the same side that it started from. So there you go. That's a free end reflection. Since this part is free to move, when this pulse meets it, here it goes again, it causes the endpoint to rise. And then it comes back down, and the wave stays on the same side of the baseline. And there it goes. Now, when it gets to the end, that's a fixed point again. So, like the first example, it flips, reflects, up, free end reflection, same side, return, reflect over a fixed point, it flips and returns. And these are the different kinds of reflections I wanted you to be able to understand. I hope you enjoyed this video on reflection of waves. I hope you enjoy this video on the reflection of waves, and I will look forward to seeing you in the next one.